Okay, this is the geometry lecture for section 1.2, measuring and constructing line segments. The objectives of this lecture are to use the ruler postulate, construct congruent segments, and to use the segment addition postulate. A postulate is a statement that describes a fundamental relationship between the basic terms of geometry. Postulates are self-evident truths and therefore do not need proof. Postulates are also called axioms. The ruler postulate states that the points on a line can be matched up to the values of a real number line. The values that correspond to each point is known as the coordinate of the point. Further, the distance between 2 points is the absolute value of the difference of the coordinates. If we look at image 1, we see that point J is lined up with the 0 value on the ruler, and point K is lined up with 4. So the distance between J and K can be found by taking the absolute value of the difference. If I do 0 minus 4 and get negative 4, well then the absolute value is positive 4. And if I do 4 minus 0, I get 4 and the absolute value is positive 4 still. Notice in image 2, it's the same line segment. We've just shifted the ruler so that J lines up with 1.5 and K lines up with 5.5. Again, 1.5 minus 5.5 would be negative 4, which the absolute value is 4. And 5.5 minus 1.5 would be positive 4, and the absolute value is still 4. So it doesn't matter the order of subtraction, because we will always apply the absolute value to correct the sign to be positive. Remember, all measurements of geometric figures must be positive. So our first step in constructing a congruent line segment is to use a straight edge. Straight edge is a ruler. We just flip it over to the side with no measurements so that we're not using any type of predefined measure system. And you just draw a straight edge along it, and you put a point at one end and call it C. You can see that our straight edge is longer than AB, but we're going to correct that with the compass. Now we open up our compass on segment AB to get the length. And once we've set our compass, we can move it to our straight edge, putting the point on C, and we make a small curve, and that curve will be the location of D. Now we can say that segment CD is congruent to segment AB. I have a YouTube video where I go through constructing congruent line segments with compass and straight edge. Just follow the link below. The segment addition postulate. If a point B is between A and C, then AB plus BC is equal to AC. The converse of this statement is as follows. If AB plus BC is equal to AC, then we can say a point B is between points A and C. At the bottom, I put a note that these points must be collinear and that point B must be in between A and C for these statements to be accurate. Since A, B, and C are not collinear in this example, AB plus BC equals AC is not true, so we have the not equal to sign. That is because A, B, and C are not collinear, and side AC would form a triangle, and it would not be a true segment addition statement. In this second example, B is not the in-between point. So if we took AB plus BC equal to AC, it would be false because AB and BC are two larger segments. How could they possibly add up to be a smaller segment? Let's practice these concepts with some numeric examples. So if you look at example A, we have a segment DF with a point E in between, and we want to find the measurement of DF. We can do this by first writing the segment addition statement, DE plus EF equals DF, and then substitute the values 23 and 35 into their appropriate segments. So you see I've done that here. DE was replaced with 23, EF was replaced with 35, and since they're on the same side of the equal sign, we can simplify by combining, and we get that DF is 58. If we look at example B, we can again begin with the segment addition statement. FG plus GH equals FH. Once again, we substitute our values into the segment addition statement. Notice this time the constants 21 and 36 are on opposite sides of the equal sign, so we must subtract 21 over to the right-hand side. That gives us GH equals 36 minus 21, which simplifies to GH equals 15. Here are some algebraic examples. Again, start with your segment addition statement, then substitute into the segments, and then since our algebraic statements are both on the left-hand side of the equal sign, we can simply combine and simplify, and we get that AC equals 8x minus 1. With example B, again, we start with our segment addition statement, but when we substitute in, we see that the algebraic expressions are on opposite sides of the equal sign. So we take 8y plus 5 and subtract it from the right-hand side. Notice the arrows that are distributing the minus through the parentheses so that 8y plus 5 become negative 8y minus 5 in the line below it. And since everything is on the right-hand side of the equal sign, we can combine and simplify, and we get that QR is 5y plus 20. So here's a problem that you may see from a textbook, and your first step here is going to be to draw out the problem. They've told you that point S is between points R and T, so we've simply drawn that out. Now we can continue with our segment addition statement, and then we can substitute what each statement expression is from the given box. And the rest is to combine and simplify and solve for x. Once we get that x is 5, we can plug it back into the expressions to find that RS is 20, ST is 1, and RT equals 21 was one of the givens. Here, you're given the segment drawn out. It may not be to scale. Just never assume that AB has to be smaller than BC. It's just simply telling us B is between points A and C. And in this one, we have a bunch of quadratic expressions. So we'll start by writing our statement and then substituting in. Let's combine the terms on the left-hand side first. And since we have a quadratic from algebra, you should recall we always get 0 on one side when we're solving. And if we recognize this as the difference of two squares, we can factor it as 2x plus 3 times 2x minus 3. And let's continue on another page. We will now take each factor and set it equal to 0. This is known as the zero product property. So 2x plus 3 equals 0 will give us the solution x equals negative 3 halves, and 2x minus 3 equals 0 will give us the solution x equals positive 3 halves. Now we must find the measurements of sections or segments AB, BC, and AC using each of these values. So when x equals negative 3 halves, we get AB is 15 halves, BC is 6, and AC is 27 halves. When x is equal to positive 3 halves, we get AB is 21 halves, BC is 3, and AC is 27 halves. This concludes this lecture. If you have any questions, send them to me. Complete your assignment that's been posted, and subscribe to my channel to continue to receive updates of future videos that I post, and to be able to follow the links of the videos that I've connected to this one, such as how to construct a congruent segment.